Section 9.4 is called odds and expected value. Have you heard either of these phrases used before? And if so, in what context? What are the odds? So when somebody talks about something bad happening, where else? Yeah, expected value usually has to do with money. It doesn't have to, but that's where it's usually used. Yes, expected value, the expected outcome of something happening in terms of money. No one else has heard odds anywhere else. I know you guys have. It's in the Hunger Games, and when I used to use this example, nobody even said that, and now everybody will. From here till now, I don't know, till forever probably. There's another place odds is used a lot. You guys are all so innocent, you would have no idea. In casinos, often in horse racing, is a really key example where people talk about the odds of a certain horse winning. All right, so we're going to take a look at these different descriptions today. So we're going to start with odds. Odds is like probability, but it is not the same as probability. Okay, so when we do probability, we are comparing the likelihood that something happens compared to anything happening, right? So when we say there's a 50-50 chance, we say there's a 50% probability, right? Or a 0.5 probability. You're comparing the likelihood that it happens to anything else happening, any outcome at all. Odds compares the likelihood that an event happens to the likelihood that it does not happen. That's the difference. So when we take a look, what we're actually comparing is if the probability of event A is P of A, then the odds of an event happening is P of A, divided by P of A complement. So it's likelihood that it doesn't happen. So this is what we mean when we say 50-50. There's a 50-50 chance. 50% it does happen, 50% it doesn't. Okay? That's where you've seen it used. And it doesn't have to be written as a ratio. You can have it written like a ratio like this too. We're going to be working with it mostly in terms of a fractional point of view, but it can be written as a ratio with a colon between them, and that would be fine. An equal way of writing this would be writing it as 1 probability of event A divided by 1 minus the probability of event A, because probability of the complement is 1 minus the probability of the event. And we've encountered that in a couple of sections now. Now, this is the odds of an event happening, like the likelihood that it will happen. The odds against is the likelihood that it doesn't happen. And all you have to do to get this is to flip all your fractions upside down. So it's the likelihood or the probability that the event doesn't happen compared to the likelihood or the probability that it does. So it'd be 1 minus the probability of A divided by the probability of A. And we saw this happen back in Chapter 6. We did an example in class where we talked about comparing the number of girls in the class to the whole class and the number of the girls in the class to the number of boys in the class. Do you guys remember that example? The comparisons were simply comparing different things, girls to whole class compared to girls to boys. The girls to boys is actually an odds kind of question. The girls to the whole class would be probability. And we're going to do an example of that just like that here next. So we've got a set of 8 marbles. We've got 5 red, 3 white. Okay? So the first question has to do with probability. What is the probability of choosing a red? Right, 5 over 8. There are 5 red marbles, and there are 8 total. So it's always comparing it back to the total when you're doing probabilities. When you're doing odds, so we'll write O of red for odds. You still have your reds on top, 5. But instead of comparing it to the things that are a total number of, in this case, marbles, we compare it to the number that are not red. In this case, they happen to all be one same color. That's fine. But it's giving the opposite argument. The number that are not red, it would be the number 3. So the odds are 5 to 3. The probability is 5 to 8. 5 out of 8. The odds are 5 to 3. 5 do, 3 don't. 5 match the description, 3 don't. We can do this with things that are also not random selections of things. We can do it with something where we know probabilities as well, like when you look at your phone and we talk about the probability of a chance of rain, or when you watch the weather channel. Does anybody watch the Weather Channel for their weather forecasts yet? No? I haven't in years, so got my phone. That's where I get my weather right there, or my husband who looked at a phone. So, all right, so here's an example of one that has that kind of a feel to it. This is the probability of the chance, the probability of it raining for the day is 60%. And we want to know the odds against. So the first thing I'd like for us to do is to simply write down, if the probability is that it rains is 40%, what's the probability that it doesn't rain? Yeah, it's 40%. Of course, this is actually more like a percentage, but that's okay. We can still work with it the same way. So the probability that does rain is 60%. The probability that doesn't rain is 40%. That's information given to us about probabilities. We need that information in order to do the odds question. So this is odds against it raining. That means it's the odds that it doesn't rain. Does that make sense? Odds against raining means odds that it doesn't do it. So this is a ratio. And what we want on top is we want the probability of it satisfying the category we're in. Our category that we're trying to find information about is about it not raining. So what goes on top is the likelihood that it doesn't rain, which would be the number 40 on this one. And then the likelihood that it does rain would be the number 60. And then if we reduced this, what would we get? 2/3 is correct. Very good. So the the odds against it raining, or the odds that it doesn't rain, is actually 2 to 3.
So we don't need to worry if there's like a percent under like.
Well, they would cancel out. This is like a fractional thing.
Okay.
Yeah. So it doesn't end up actually mattering. You're right.
Okay.
Mm-hmm. All right. So we kind of already talked about this a little bit, but we're going to write it down a little bit more formally. These are the odds of an event happening, and these are the odds against an event happening. This should say event, not event E. Even E. Event E. Okay, so if the odds of event E are m to n, then the probability is m over m plus n. And if the odds against are m to n, then the probability is n over m plus n. I'm not a huge fan of formulas. I think that you probably could have figured this out without me writing down m's and n's everywhere, and now that I wrote m's and n's, you're going, what? What happened? Because there's lots of m's and n's, and we weren't even talking about m's and n's. We should have brought M&Ms to class, shouldn't we? Yeah. Okay. Next time, maybe. All right, so let's take a look. So what this is actually saying is exactly what we did above, all right? So let's say, for instance, we had some numbers here. I'm going to do the marble example that we just used. So back when I did the marbles, there were 5 red and there were 3 white. Is that right? Okay. So the odds of here drawing a red marble were 5 to 3. We'll write it in their notation that they did here. What that is saying is that I had a 5 over 5 plus 3 probability. Because all m plus n is the total number of things that could happen. Okay. That's all m plus n is. And then m is the desired outcome. It's what we wanted to have happen. That's my 5 reds. And then below, if we had the odds against the event happening, then again 5 to 3. But now we want it to be against, then that's the 3 over 5 plus 3.
But doesn't that make it probability?
It is. This is probability. You're exactly right.
Oh, I didn't see that.
Yes. Yes. And that's a good thing to notice, is that they're going back and forth between talking about probability and talking about odds. So what this is doing is it's trying to give you a relationship sort of setup of the two things. The reality is, once you have numbers to work with, the setup's pretty natural. You just have to remember what you're comparing. Are you comparing having something to not having it, or are you comparing having something to any possible outcome? Because that's the difference. So let's see. We have one more example about odds. We'll do this one. This says to consider a 3-child family. I drew a diagram of a 3-child family not too long ago, didn't I? Yes, I did. And when we drew that 3-child family, just the fact that you're having 3 does not mean there's 3 branches. Remember, each child has 2 branches because it's talking about gender. This question wants to know the odds of having the same gender of children. So I'm going to draw the diagram again. I'll draw it going downward this time because of the way that I've left myself space. So here's child number 1. They're either a boy or girl. Child number 2 is either a boy or a girl.
When we do this on our homework, are we going to have to do another tree?
If you're working with a new problem, yeah.
Okay.
I don't think you have a 3 case children thing.
Okay.
So here's my boy girls again. And it's all 50-50, so we'll write in there the 0.5s on everything. Now, this is the diagram. We haven't actually answered the question that I'm sort of taking up all the space to do. The question said, what are the odds of having all the same gender of children? Well, let's take a look. Where do I have all the same gender of children? Where are they? On the edges at the moment, right here and here. So I can figure out that each one of those is actually 0.5 times 0.5 times 0.5, which is 0.125. And we did that calculation before, so I'm going to assume that that's all okay for finding that, 0.125. So if I'm wanting to know the odds of having all the same children, same gender children, this would be the probability of the same gender. Odds compares it to the probability of them being not the same, right? So the probability they are the same is 0.125 and 0.125 combined together, which is what? 0.25. It's addition, so it's 0.25. Very good. So there's a 25% chance that I have 3 children that are in fact all boys or all girls. So then what's the likelihood that I have 3 children that are not all boys or not all girls? 0.75. Do you have to actually multiply those out? No, you shouldn't, because it's just 1 minus the 25%. Now we can simplify this ratio. So what is 0.25 divided by 0.75? It is 1/3, yes. So the probability, I'm sorry, not the probability, the odds of having all the same gender of children is 1 to 3. Or if you don't like the written as that way, you can write it as 1 to 3 like this, of course, too. That's fine. Now, part B is a really simple, clean question after having done part A. Because how is B different than A? Yeah, it just says against. So do you know what we do when we do odds against? We flip a fraction upside down. We don't even have to do 1 minus. We just flip it upside down. So if the probability for having this certain thing happen was 1 over 3, then the probability against is 3 over 1, or you can write it as 3 to the 1. 3 to 1. We have 3 to 1 odds of having children, against having children that are all the same gender. Yes?
How did you get the 0.25 and 0.75? I missed that.
That's okay. The 0.25 came from adding up the 0.125s on the edges. Each of those 2 branches gave me a sum of 0.25. And then we got the 0.75 because it's the leftover piece. It's the other 6 branches that we didn't multiply together. Since they all have to add up to 1, we can all just take 1 minus the 0.25 to get 0.75. Any other questions on this one? All right. Expected value is the other sort of topic in this chapter, or section of this chapter. And we talked about before we actually jumped into this section that it does relate to money. And so you're going to see a lot of situations in this one where we're going to be talking about money because of the context there. So first says expected value. If we have A1 through AN possible outcomes, so just whatever they are. So maybe you have 6 because there's 6 rolls of your dice. Maybe you have 2 because it's 2 different things that can happen when you flip a coin. So whatever the outcomes are, we're labeling them like this because we don't know how many. A1, A2, A3, however many there are. Okay? The probabilities go along with them, so they have the same subscript. So the probability of event A1 is P sub 1. The probability of event A2 is P sub 2, and so forth. So it's just a corresponding written out organizational tool is what it is. Then the way that we calculate expected value is we take the probability of event A times the event A1. We take the probability of event 2 times the event A2. And we keep multiplying the probabilities times the events until we get to the last one, however many there are, in our event list. So this problem and this process really, it's just involving multiplication and addition. That's all that's really going on. But you do have to find the initial probabilities, which we've been working on in sections 1 and 2 already. And then we call a game fair if the expected value is 0. Okay, if its expected value is 0, the event is called fair. And we'll get into a little bit more of fair events very soon. So let's do an example. Example number 4. On a roulette wheel, there are slots numbered 0, 0, 0, and 1 through 36. One way to bet is to bet on a single number on the wheel. If the ball lands on your number, then you receive 35 chips plus the chip you played. Okay, so you give them 1 chip as a bet, and then if you win, they give you back 36 chips. Your original 1 chip plus 35 more. Do you have a picture of how that works? Okay, and if you don't want to think about the chip, you can think about a dollar bill or something like that as a correlation. First question is related to what we've done before. What is the probability that you will land on space 0, 0? All the roulette wheel sections are equal angles, so what's the probability you land on 0, 0?
1 out of 38.
Right, 1 out of 38, because there are 38 different slices of the pie, so to speak, right? So here's my fun example that I told you was coming. This is a real-life example that happens in my family. My in-laws will occasionally go to casinos. I don't think they're bad people. They go kind of like when you guys go to an arcade or something like that. You go to the mall to spend a little money. They go with the intent that they're going to spend a little bit, they're going to leave. They're not addicted or anything like that. But they'll occasionally go to a casino. My father-in-law really likes to play card games, but if he passes by the roulette wheel, there is a board that sits right beside the roulette wheel that tells you the most recent wheel spins. It tells you it spun 6, and then it spun 15, and then it spun 32, and then it spun 0, and then it spun 5, and then it spun 12. It just tells you what it spun for the last so many spins. Okay? So he walks by this board, and he looks at the board. And if the board does not have a 0 or a 0, 0 on it, which is slightly different than the way I've set up the problem, then he decides that he'll bet. Okay? So let's actually do the problem the way that it's really worded now, because I simplified it a little bit for calculation purposes. So when my father-in-law passes the roulette wheel, it says if he sees that it has not landed on 0, 0 in the recent history on this board, he'll bet on the number 0, 0 showing up. If he bets 1 chip and it's worth $10, the question is, what is the expected value of his bet? And then it says to explain. So let's talk about what happens here. He's betting some money, and there's really only 2 outcomes. What are the 2 outcomes? He wins. He loses. I mean, those are the 2 things that can happen, right? So we have 2 probabilities. We have the probability that he wins, and we have the probability that he loses. So let's talk about the probability that he wins. What's that? What's the probability that he wins? Is it 1/2? 1 out of 38. It's the same thing we got from part A. All right, that's the probability that it lands in the 0, 0 because that's how he's bet it. So then what is the probability that he loses?
7 out of 38.
Like almost all the time, right? That's what that says, 37 out of 38. Pretty much guaranteed you're going to lose. That's what that says. All right, so the expected value then takes the probability of winning, 1 over 38, and it multiplies it by how much money or what your net change is going to be when you win. So let's talk about what happens when he wins. Let's say he really does win. How much money does he win?
$360.
Does he win $360 or does he win $350?
Well, it says you receive 35 chips plus the chip you played.
True.
So if you played the chip, it'd be 36.
You're right in what you're saying, but it doesn't work for what we're working with because it didn't really win the money he bet. That was his money to start with. So when we're looking at the value here, we're kind of looking at my pocketbook. How did it change before versus after playing the game? Do you guys see? Okay. If I paid $10 to play, then my wallet has $10 less in it than it was before. So when they give me $360, that $10 kind of goes back where it shouldn't have left, basically. I really only win $350, right? Because that $10 was just compensating me for what I played. It didn't cost the casino. That $10 didn't cost the casino to give it back to me. What cost them was the $350. So when we win, we actually win in this scenario $350, not $360.
Is it 350 because you bet $10 and I take 10 times 30?
Yes, exactly. I should have mentioned that. Hannah did that in her head too. Yeah, it's each chip's worth $10, so we're getting $350 because we're multiplying the 35 chips times the 10. Yes, thank you, Allie. All right, so we're going to add to this the probability that we lose, which is 37 out of 38. What happens if we lose? Try again. I heard like a dozen people answer. What happens? You're out $10. That's really important, Allison. So it's not zero, right? You actually have $10 less than before you made the bet. This is negative 10. That is the cost to you. It's negative. I can't spend that $10 on anything else now. It is gone. So it's a negative outcome on that particular case. So grab your calculators, and I want you to multiply 1 over 38 times 350, 37 over 38 times negative 10, and find out what you get. So you're going to get and we are talking money, so we do need this in a numerical, like decimal form with money. We are going to get a negative. We'll talk about what that means, but negative something. So what do you get for this? Right. All right, so let me tell you what this means in terms of expected value. In terms of expected value, in the explaining your answer business, this means if we did this a large number of times, over the long haul, on average, we would lose 53 cents every time we played the game. That's what this is saying, right? Like, obviously, if we win at some point, that's great, and we've got $350. But on average, we're losing 53 cents every time we play. This is why the casino stays in business. If they couldn't make any money doing it, they wouldn't be doing it, right? I mean, that's the point. They have to be winning more of the time than they're losing, at least numerically in terms of cost value, or they can't have the big hotel. And they can't give you the free food that they give you and stuff like that at the casino. So this is what's happening. We are losing 53 cents every time we play the game. So write a little jotted something down here where it says explain your answer about what that negative 0.53 means. I tell this story and I chuckle when I do it because does this make sense? I don't mean in terms of being the number at the end. Does it make sense to bet on the number because it hasn't appeared in recent history? Why not?
Because it's still likely that it will or won't.
Right.
It doesn't change.
It's an independent event, just like the ones that we were looking at with the person who was talking about flipping the coins 3 times and thinking that it's not a fair coin, right? Every event is independent. Doesn't matter what happened in the recent history. That changes nothing about what's going to happen next. So this one is an example of that going on. Let's do another one. This isn't really quite described right, and so we'll make the change to it as we go. But it says, in the television show Deal or No Deal, do you guys know this show? Okay, good. Deal or No Deal, a contestant is down to 2 cases with equal probability of being chosen. The cases have $250,000 in one and $1 in the other. If the game is fair, and I don't mean here fair as in a fair game where the expected value is 0. I mean fair in the sense that they're going to give you what is a fair amount. Okay, so I'm using the word fair differently than the description in this section. I just want you to be aware of that. If the game is fair and you're the banker, what would you offer the contestant as a deal? So we're going to calculate an expected value here. And the probabilities are what? What's the probability that you have the $250,000 case? 1/2, right? Or 0.5. Because it said equal probabilities. And what is the value you get to take home if you have that case? $250,000. The government's going to take half, though, so, you know, I'm just saying. The other one also is a probability of 1/2, and if you have that wonderful $1 case, that means you get $1, yes. All right, so we're going to calculate the expected value of what we would expect the banker to offer us, more or less, if we were playing the game and the game were quote-unquote fair. What would you get? We'll go ahead and calculate what it really says. What did it say after that, Allison? Yeah. I know that they don't play the game with sense in it, so to speak, but this would actually be the expected value, truly, the way that we've worked this out. So if we're playing the game, our expectation is that we're looking at roughly $125,000 offer on the table to decide. Okay. Yeah. Any questions on that one?
So could we say 125,000 and cents, or would we need to say it should be less than that so they can still?
Well, but we're talking about the game being fair, not them making money. In fact, nobody's making money on the game show because you're not paying to play. So we don't have to worry about that in this case. All right. This is a fun one, too. There's a cartoon in your book at the beginning of this section about the lottery. And it talks about the odds against winning the lottery. So the odds against winning the lottery in that cartoon example are 55 million to 1. It just makes me smile. But man, somebody's got to win, right? No, they don't. All right, what is the probability of winning the lottery? Okay, so what is the probability of winning the lottery? 1 out of what? 55 million 1. Oh, you guys are really on top of it. You've got the and 1 in there. It really is and 1. Because this right here are odds, right? So you've got 55 million people lose, 1 person wins. That's what that odds means, the way that it's written. So your probability of winning are 1 out of 55 million 1. So let's see what happens. If the grand prize is $13,567,290 and a ticket costs $1, the question is the game fair? And we are using the word fair here exactly like it's being used in this section. Okay? That is, what does it mean for a game to be fair? Do you remember what it said?
The expected value is 0.
Yeah, the expected value is 0. So what we're going to be testing out is what the expected value is and deciding if that's the same as the number 0, you know, if we get 0 out of it. All right, so the expected value, there's only 2 things that can happen, right? You can win or you can lose. So we already calculated the probability that we win. It's 1 out of 55 million 1. What happens if we win? Careful.
$13,567.
Yeah, your decimal's off. 13 million is what you meant.
Yeah, sorry.
It's okay, $13,567,290. Or do we?
Wouldn't it be 89?
Yes, 289. Why 289?
You lost 3.
Yeah, you paid $1 to play. So it may not seem like a big difference, but yes, it would be 289 at the end, not 290. Okay then, just in case you were thinking about doing this, what's the probability that you lose? 55 million to 55 million 1. Yes. And what happens to your net worth, if you will, if you lose? It's -1. Okay? So grab your calculator, calculate this all out. and let me know what you get. Do you get 0? Do you get a positive? Do you get a negative? And what does that mean in terms of the game? So what do you get? And it's money, so we're going to 0.75, okay? So if we played this game a whole bunch of times, what happens on average? We lose 75 cents every game on average that we played. Is it fair? No, it's not fair. It's not a fair game.
Does that mean that it's like, it's more towards like the other thing? Like,
It's a very good question, and you're exactly right. If the expected outcome is negative, it means the person who took your money to play is benefiting from it. So for them, it's a positive 75. For you, it's a negative 75. So on average, what's happening then is that every ticket that's sold nets whoever's selling it 75 cents. Compared to losing you 75 cents each time you play. I have one slide left that talks a little bit more about this. Or do I? Okay. I think it must have gotten erased on here. It's on your paper, though. Part C. I'll put it back in later. I'll read it, too. So it says, as with many state lotteries, the proceeds are often said to benefit education. Have you ever heard that before?
yes.
Okay, they do that a lot. They'll say that. Under these conditions, if all proceeds benefit education and 1 million tickets are sold, what is the expected value generated for education from the sale of lottery tickets? And this actually goes right hand in hand with what you asked me, Allie. So the person selling it now, in terms of the context from Part C, is the state, who is collecting it for education, supposedly. And they're collecting 75 cents off of every ticket sold. So if they sell 1 million tickets, what's the benefit to education? 75 million. So it's that 0.75 that we got from the previous part. And we could write out all the decimals more if you wanted to. If you don't, that's fine as well. But it's times our million. So we have 0.75 times 1 million, which isn't 75 million, but it's what? I think it's 750,000.
Yeah.
Is that right? Did I get my decimal in the right place? So the benefit to education is 750,000 on average. Okay, because we used that 75 cents as the on average amount. Part D really tells you, though, what's really happening. Part D says, what are the actual possibilities of amounts applied toward education? There are two possibilities. One possibility happens when no one wins. If no one wins and 1 million tickets were sold, how much money is generated for education? Nope, because that was the on average one. Yes. We have $1 per ticket. We have 1 million tickets. So if no one wins, we have $1 million generated to go towards education. So if you really are wanting to support education, then you should really want no one to win the lottery. That's what that says. That is not how people play the lottery, is it? No. The other possibility is that someone wins. Winner, winner, chicken dinner, right here, winner. So what happens then? Well, you still brought in $1 million, but what happened after that? How much?
No, wait, 13,567,000.
The 290? Yeah. So if someone wins, which is the reason they played the lottery, they did not play the lottery to give money to education, guys. They did not do that. If they played it to win, then this is the situation they're hoping will happen. They're hoping they'll win. If they do, what happens to this number? It is negative 12,567,290. You cannot hold both of these views at the same time. Either you're supporting the education and you want everybody to lose their money, or you're not supporting education because you want somebody to win, in which case education is now negative. Less money than they had before. This seems ridiculous, doesn't it? And this is what they do all the time when they're trying to promote things like the lottery or casinos. They did the same thing when we were living in Ohio. They wanted to grant rights for people to start opening casinos, and they were doing the same kind of thing where they were talking about benefiting education. It's an interesting argument.